Welcome back guys to day 8 of Advent of Code. So in today's question, we find ourselves on the roof of a top secret Easter Bunny installation. This is some scam place where they have huge antennas which are emitting a signal which will make people likely to buy some chocolate as a Christmas gift. But the likeliness will only increase by 0.1%. With enough antennas, I think they can make you 100% likely to buy it. So it's very scammy, but anyway, we have to help them. So the puzzle input is something like this, in which we have multiple different antennas. Each of these antennas are emitting some frequency of signal, and the different, like these, it can be a number, it can be a small case letter or an uppercase letter, and each of the unique letters represent a certain frequency. So now every pair of antennas will have something called an antinode, and how that works is, if you have, suppose in this example they've shown us how that works. If you have these two antennas, so from this antenna to distant antenna, whatever is the distance, at the double distance of that, the antinode will be present. And similarly from this to this, whatever the distance is, at a similar distance, the antinode for this combination like this. So it works both ways. But if these antinodes go out of the map, it doesn't matter. So we have to do that for all of them. So like here we have 3 pairs, so we have 4 antinodes plus 2 more, but those 2 are out of the bounds of this map, so we don't count them. So we have to actually look at how many total antinodes are being formed based on all the frequencies that exist. Okay, so that is one thing. And the other thing is, suppose there is, like, this is the edge case that they've cleared for us. Suppose there is an antenna at the location where the antinode is supposed to be present, then both can coexist, the antenna and the antinode for the other antennas. Okay, so let's solve this. It shouldn't be too hard, but let's see if my logic works. Okay, so not a very hard problem, just that I had this edge case which took me some time to realize. If 2 antinodes exist at the same location, we're just going to take the unique ones. That was one of the things. I think they might have mentioned it and I didn't read it properly. But anyway, here process input is the same thing, splitting by new line, and for each character we get a sort of a map like this, or 2D array. Then we find the antenna locations for each of the type of antenna. A, 0. In the W we only have A and 0, so we found the map here, the locations here in a dictionary. So for A, we have all these locations. For 0, we have all these locations. So we are just doing that in a double for loop. And we are skipping whenever we see a dot. Anything else should be a character. I'm hoping they haven't added, we should just check actually. They've not added some special other types of special characters which we can't consider. Okay, so that's cool. We don't have to worry about that. Another way would have been to check if it is a alphanumeric character, because they have told us that it will be one of those. Then we have to find the number of antinodes, in which we just keeping a track of the antinodes as a set, since it's supposed to be unique. This was something for me to debug later. Antinode location, what all the antinode locations we found, but now that we have a set, we don't need it. Then max, this is the maps bound. If anything goes outside this, then we don't need to count it. So this is the max I and j. Antenna frequencies, they are the keys of all the keys in our dictionary that we made, the antenna locations. Then for each of the frequency, what we are doing is we are taking the location, and if the locations, the number of locations in this frequency is 0 or 1, then it doesn't make sense to check with anything else, so we are just returning 0. Oh, this can cause a problem. If we return 0, it'll just finish this method. No, it's a good thing we found it out as I explained it. Okay. So yeah, if the location length is not 0 or not 1, that's when we can do this. The for each loop doesn't allow us to continue and all that. Sort of annoying, but okay. Then we are doing a double for loop again, in which if the I and j, meaning the same antenna, it's not the same antenna, then we check the distance and we find the new antinode location by adding the distance that we have found to the first location. How this works is, let me show it here. So suppose we have some x, we have x here, then there's 2 points, and then there is x again, and then there is, let's just assume 3 points here, 3 points here. So this is 0, 1, 2, this is 3, 0, sorry, whatever, 0, 3, and 0, 3, and this is 4, 5, 6, so this is 0, 6. Now if we do this minus this, then we get 0 and minus 3. So if we add that to this, we will get 0, 0. So this will be one of our locations. Similarly, if we subtract this to this, then we will get 0 and 3. So we'll add it to this, and then we'll get 0, 9, which will be our antinode here. We are doing that the same way, except we can have something here and then 2 dots, and then we can have 6 here. So this is 0, 0, this is 1, 2, and we are doing it the same way. That will work for all the combinations. So that's how all this goes. And if the new location is within the bounds, then we add it to this set. The set will keep track that there's only the unique values. This was for me to debug. This is the edge case I had just thought of, so that's why I kept this. Then we are returning the size, and we're getting this, we're getting 14. So now let's try it with the actual input. Code is definitely not efficient. O of n cube is bad. Shit, I keep forgetting to share my screen when I do this. Okay, so we've submitted it and we've got the right answer. Now let's see what the challenge is for part 2. Okay, in part 2 what we're doing is, they've told us, now suppose you have this 2 antennas, then you find this antinode, but that doesn't just stop here. You go on and add another antinode till whatever bounds are possible. So you have this and this, so you should get this, and then you get this, and then you get this, and then it'll go on. So that way we have to find, if this goes on, then we have to find the number of antinodes, and in this case we have to include the antenna positions also, because they are also in line of with these antinodes. So that means even this is an antinode, and even this is an antinode, even this is an antinode, and so on. But I still have sort of a confusion. What if this t existed here? So now only these two are in line, so does that count or not? They have sort of said something about it. In fact, the three T frequency antennas are all in line, all exactly in line with two antennas. So they are all antinodes. Confusing. Let's try it. Okay, for part 2, there's not much of a change that we had to make. We just had to add this part, which is adding all the antinodes to this set. I actually messed up with the syntax here, and then that took me a lot of time to debug. We cannot add an array to a set so conveniently. Even with even by using the spread operator, we have to add them one by one. At least that's what I learned so far. We'll see if there are any other ways after this. This counts found is of no use. I just had that again to debug, and I mean, yeah, I messed up with that a lot. So that's one thing. And then instead of checking the if condition here, if it's within the bounds, we are checking while this is true, we will keep adding the antinodes which we are finding, and use the new antinodes and add the distance to this new antinode and push that also. We'll keep doing that till it goes out of bounds. And so we will print the size. We're getting 34, which is the expected result. Now let's try it with the actual input, and this will be very inefficient, so it might take some time. Oh, that is instantaneous, but this is very inefficient anyway. Now before I forget, I should share my screen. Oh great, it is not so hard. I think I have an issue with writing bad code. Cool, so we're done here. Let's see tomorrow's question. See ya guys, bye.